All right, let's give this a try. We are beginning our last unit of the year, Unit 10, on circles. All right. I know that was a quick unit on volume and surface area, but you can still practice it, and we will. But let's talk about circles before the year is over, because this is actually what Euclidean geometry, this is what he started with. For some reason nowadays we end with circles. You know, the compass and the straight edge, the compass makes a circle, and then circles can make all these different sorts of shapes with intersecting circles. That's what Euclid figured out. You can study more about that. Let's look at some of the properties. So with circles, start out with very basic. We have a center. We have the circle itself, which is a distance around the center. We have the radius, as you know, the diameter. Okay, also we have what is called a chord. So a diameter is a chord that goes through the center, but there are all sorts of chords that go from one part of the circle to the other. If they don't go through the center, they're just not a diameter. Radius is not a diameter chord because it starts at the center and goes to the edge. Also, we have a sector of a circle. A sector of a circle is like a pizza slice. And we have arcs on the circle. Arc is like going around the circle. So the chord's going across the inside of the circle. The arc is taking the way around the circle. We have minor arcs. This would be a minor arc. And then a major arc is going the long way around. Major arc. And we have ways of naming these arcs. Let's say we have these points on the circle, A and B, and maybe C is around here somewhere. So the minor arc, AB, would be like this, A, B, and we put a little arc over the top. And the major arc would be A, C, B. So we know if we want the major arc, we just denote that we're going to go through the point C instead of going the short way. All right, so those are the arcs. So we have sectors, chords, diameters, radii, minor arcs, major arcs. We also have angles in the circle. So let's start with that. Angles, and there are two kinds of angles in the circle. There are the angles. Let's call them theta. Remember theta? This is called a central angle because it's an angle formed at the center. All right, should make sense. And the central angle has this property about it. If this is a 60-degree angle, let me write it out here like this so you can read it. Let's say theta is 60. Then the minor arc intercepted here is also 60. So we know all the way around the circle is 360, and we measure arcs in degrees. And so there's the central angle is an angle, and that's 60 degrees. And then the arc is also called 60 degrees. It has a length, an arc length, which you may be thinking, wait a minute, what about the arc length? So arcs, let's write that down. Arcs have measure and length. All right, let's just get that straight. And so we have the central angle. and the arcs intercepted by it. And then the last thing we have is these things called inscribed angles. Inscribed angle. Inscribed means to be written on, or on something. And so inscribed angle is on the circle itself. And here's the relationship. That angle is x. The arc it intercepts is actually twice. Okay, so a lot of good information there. So, and we can add arcs together, just like we can add angles together, we can add arcs together. So let's do some calculations. What is the arc measured, minor arc AC on the circle P? So AC, so we're talking about that one. And we know that we have all those arcs there, right? Let me just get my calculator here. Okay, so let's add 136 plus 74 plus 42. What's that? 252. So I added all these together and I got 252. Is that what you got? Okay. And then we don't know what these are, but they're the same. So let's call them X and X. So that means that we know 2X plus 252. What's it equal to all the way around the circle? 360. So now we're going to solve for X. So it's 108. So 2X equals 108 divided by 2 divided by 2. X equals 54. 54. And so what is the measure of AC? It's going to be, actually, we could just, so we know this is 108 and then the 42, right? Uh-oh, baby's crying. Check that. 150. It's one. All right. So now the circumference, what is the central angle of the arc in degrees? Okay. Central angle has a circumference and the arc length. So now let's talk about arc length. That is a formula. Arc length. So we talked about arc measure, right? So now what about that length? So all the way around the circle is the circumference. And what is the circumference? You should know it's 2 pi r or pi d, pi times the diameter. And so arc length is going to be the measure of the central angle. So you see that central angle there divided by 360. So it's like a percentage, right? And then we just take that percentage and we multiply it by the circumference, 2 pi r. And that's how we do it. So what is the central angle? Well, they give us the arc length here. And that equals arc length. Let's call the arc length. Let's call it something. Let's call it L. I don't really know what the letter we use. So let's just call it L. Okay, so L equals 17 thirds. 17 thirds. We don't know theta. We're going to figure it out. But we do know, what is this, 6? Okay. So we don't know the radius either. That could be a tough one. Oh, the circumference is 6. A circle has a circumference of 6. So we can use that to figure out the radius. Okay, so the circumference is 6, so 6 equals 2 pi r. And so divide both sides by 2, and we get 3 equals pi r. Divide by pi, and we get r equals 3 over pi. Oh my. R equals 3 over pi. So, oh, but then the other thing is we know the circumference is 6. And so that's the circumference. So we could just put a 6 there. So that was a nice little calculation, but we don't need it. I'm just thinking through the problem. So now we know the circumference is 6. I've put 6 in for the circumference. And now I'm going to solve for theta. And I'm going to start by, let's put the 6 up there. You know why? If I do that, then I can cross multiply, and I love cross multiplying. I have a fraction equal to a fraction, so that's how I know I can do that. What's 17 times 360? All right, 17 times 360 is 6,120. All right, now let's divide both sides by 18. Divided by 18, 340. This certainly does not look like 340. But if the arc length 17/3, oh, I see. That means that, yeah, this would be 340. But if they're asking me what has an arc length, what is the central angle of the arc? Of the arc with 17/3, then it's 340. But I really would want to find this little angle right here. So that angle is going to be 20. So now I'm confused. So they want me to put in 20, which appears to be the central angle, or the 340, the reflexive angle. Let's find out. No, should have put in the 340. Come on, Mr. Field. The arc has the 340. All right. Now I know. Now I have to do it all again. Okay, so what is the arc measure of the minor arc? Thank you. Minor arc. So now, okay, DE. So we're going to go D to E. Oh, that's nice. The one they didn't give us information about. What is the arc measure? Well, let's see. What do we know? We have diameters. So that means, okay. Diameters are 180 degrees. Did you know that? 180 degrees. And is BE a diameter? It is. Check it out. So we know this is 180. So we can set up the equation with these two central angles, and that would be a total of 8W, 4W, and 4W is 8W, and 8 and 4 is 12, equals 180. 8W equals, subtract that by 12, and you get 168. Divide by 8, and W equals 21. And so that's going to help me out. So if I want to figure out DE, okay, well, I can now figure out this one. So 4 times 21 plus 4 is 88. And 2 times 21 plus 4, 11 is 42 plus 11, or 53. It's 53. This is 88, and this is x. But I know again that these add up to 180. So let's add 88 plus 53 is 141 plus x equals 180. Subtract. I can see it's 39. 39. Where do I put? All right. What is the arc? Okay, so why don't you go ahead and try the rest of these? That's a lot of good information. Now let's move on to quiz 2. Convert the angle radians to degrees. Okay, let's talk about radians and degrees. Did you know there was so much to talk about with circles? So circles, you can measure circles. Draw a nice circle. There we go. So we know it's 360 degrees, but that is like, where did 360 come from, right? Why don't we come up with a measure of the circle that relates to the circumference? That is what radians are. So radians take into account that we can measure this circle as a fraction of pi, right? And so a circle, all the way around a circle, is 2 pi. And halfway around the circle is 1 pi. And how did we come up with that? Because remember, 2 pi r, and if we think of the most simple circle having a radius of 1, then the circumference would be 2 pi. That's where radians, the 2 pi comes from. Thinking about what if the circle had a radius of 1, and then we could just multiply that and get all sorts of other circles. But sometimes we see degrees. So how do we go back and forth? How we go back and forth is if we have degrees and we want to go to radians, then we take our degree measure and we multiply it by pi over 180. And then that gives us our radians. If we are starting in radians and we want to go 2 degrees, then we take and we multiply by 180 divided by pi. So just the reciprocal. That gives us our degrees. So if we want to convert this angle, which is given in radians, 2 degrees, we will simply use our conversion formula. Divided by 360 times 180 over pi. All right, notice when we do that, the pi's will cancel. Not canceling. There we go. It's supposed to be red. There. Cancel. And then let's cancel out a 0 to make things a little easier. And now let's multiply across. So 257 times 18. 4,626. Why is this pen is not working well? Over 36. So now divide that by 36. 128.5. And I'm going to degrees. 128.5. Let's see. All right. Write the formula for the arc length in terms are okay. All right. In radians. Okay. So now we got to talk about what is the formula for arc length in radians. So remember, we just learned it in degrees. So what is it in radians? It's still going to be the central angle. But remember, the central angle was divided by 360. What do you think it's divided by in radians? 2 pi. Same, just the equivalent. And then it's going to be times 2 pi r. Oh, but guess what? How nice is that? The 2 pi and the 2 pi cancel. So it's just pi r. I mean, theta r. So nice. You see how the radians can have their advantages. Okay, so our central angle, and we want to determine, write the formula for the arc length S in terms of R in the following. So the central angle is 1. Okay, so remember L is going to be our arc length. Okay, so we know 1.2 is our theta, 1.2 R, and we want to write it in terms of S. S is our arc length. Oh, I guess I can't use L. Darn. Okay. Well, all right. So in terms of S, just going to be, well, that was easy. Did more work than I had to. All right. Sector with a central angle of 200 has a radius of 9 centimeters. What's the area of the sector? Thought I'd get away without showing you the area of the sector. Well, let's talk about it. Area of a sector. So I showed you what a sector looks like. If you don't remember, it's a pizza slice. All right. So favorite food. There's a sector right there. For example, area of sector is very similar to arc length. We could take that fraction using a central angle and multiply it not by the circumference, but the area of a circle, pi r squared. That's the area of a sector. We'll call that A. Yeah, there we are. And how about that in radians? What does it look like? So again, the pi's cancel. And so we would just have theta r squared over 2. Interesting, huh? Pi cancels. All right, but we're given this in degrees, so we're going to use our degree formula in this case. What is the area of the sector? Which sector? 200? All right. 200 over 360 times pi r squared, pi 9 squared, 81. So that would be 81 pi. And then those zeros, get rid of those zeros. And then 20 over 36. So let's multiply 20 times 8, 160. Oh my gosh, that's 81. 20 times 81, 1620. Divided by 36, divided by 36, 45. I tell you, this pen is on its last leg, 45 pi. So the area of this sector is 45 pi squared, centimeters squared. Oh, goodness. All right, these quizzes. So we talked about converting. Just skip that one. Move on. Arc subtends. Central angle was the fraction of circumference as arc length. Move on. All right, you can do the rest. Okay, so cross sections. Now, before you go, Mr. Field, I'm dying here. There's too much. Cross sections are pretty simple. Okay, think about, let's see, I have this candle here. Cylinder, right? And if I were to slice it, oh, hold on, let me open up a cross section app. I opened this before. One second. All right, so let's look at these cross sections. As you can see, people have really made a lot of them, right? And it must be important. Well, they are, because this is where advanced algebra comes from. We get all sorts of precise shapes when we slice our 3D shapes. And so you can see this cross section of a cone parallel to the base makes a circle. But we can, and when we slice a cylinder parallel to the base, we get a circle. But what if we, aren't parallel to the base? Now it's an ellipse, and then we can get a rectangle, all sorts of things. And these cones, the cones can be, you gotta see the cone here, parabolas, triangles, all sorts of shapes. Very interesting. Okay, so all we have to do now is investigate what kind of shapes we get, thinking about how we are cutting it. So a vertical slice through a three-dimensional, which one of the solids can produce two-dimensional shapes sliced vertically? A rectangle. So can this one, if we sliced it vertically? Yes. How about this? If we slice this vertically, well, that would be a triangle, wouldn't it? Triangle. So only this rectangular prism would give us a rectangle when we sliced it vertically. Ooh, block of butter. Okay, so go ahead and just visualize, practice what cross section it would be. And same thing here, but now, we're getting a little bit more advanced. Like I was saying, is it parallel to the base? And so open up this. All I did was I'll put this link on, but if you just type cross section applet, then you'll go to the GeoGebra, which is where I was, and you can look at the sections of the different things, and that'll help you visualize, whether they're parallel to the base, what the height is. Okay, so that should be a lot of fun. And then the last thing we have to talk about, last 3 minutes here, rotating a 2D shape into a 3D shape. So, 3D printers are all the rage these days. They can make a lot of things. And this is some of the mathematics behind it. We're taking and we're rotating a two-dimensional shape into a solid. So if we were to rotate this triangle, what would it create? Would it create a cylinder? No way. That does not look like a cylinder. If I were to rotate it, it would be a cone, right? And what would the radius of the cone be? It would be the radius of the bottom, which would be 8. All right, what if we rotated this guy 360? Well, obviously that's going to be a sphere. If you rotated it 180, would that be a hemisphere? But 360, rotating it all the way around, and the radius is going to be 2, because the radius is 2. All right, so go ahead, give those a try. Think about what it would look like. Oh, we got to do this one. If we rotate this guy around line M, then it's going to rotate in a circle. So even though it's a rectangle, it's rotating in a circle, and that is going to create a cylinder because it's rotating in a circle. I know you're like, well, how is that a cylinder when it's clearly a square? Well, here's the answer. You don't get prisms in pyramids by rotations, because a rotation, what is our unit? Circles, right? So there's not going to be any prisms when we're rotating, because we're rotating in a circle. And what's the diameter of it's going to be 5. I mean, the radius is going to be 5. All right. So a lot of great information for you to practice and post. in the organizer.